What specific problem does the RLVR method aim to solve in the context of language modeling and reasoning?
The RLVR method aims to enhance specific skills in language models by employing a reinforcement learning objective that utilizes verifiable answers. It addresses the challenge of improving the reasoning capabilities of large language models, LLMs, by requiring a labeled dataset of question-answer pairs, which allows the model to generate responses that can be verified for correctness. The deterministic verifier calculates a verifiable reward based on the model's output compared to the ground truth answer, thus guiding the model to maximize expected rewards. This approach is particularly important as it helps to refine the model's reasoning patterns and ensures that the generated responses are not only accurate but also aligned with human expectations, thereby minimizing the risk of reward hacking that can occur with simpler reward structures. Overall, RLVR seeks to bridge the gap between pre-training and fine-tuning by reinforcing the reasoning skills learned during the next token reasoning task.
How does the proposed method or algorithm work? Illustrate step by step, particularly focusing on the reinforcement learning pre-training process and its interactions with the next token reasoning task.
The proposed method employs a reinforcement learning pre-training (RPT) process that enhances next token reasoning capabilities in large language models, LLMs. First, the model is prompted to generate multiple responses, G responses, for a given context, each consisting of a chain of thought reasoning sequence and a final prediction. Next, a prefix matching reward is calculated to verify the correctness of the predictions against the ground truth completion sequence, rewarding the model if the prediction matches an exact prefix and adheres to valid token boundaries. The model is then trained to maximize the expected reward based on these outputs, effectively reinforcing the reasoning patterns learned during the next token reasoning task. This iterative process allows the model to develop a deeper understanding of complex reasoning signals, ultimately improving its language modeling capabilities and performance on downstream tasks.
Can you provide a simple yet illustrative example that walks through the steps of the reinforcement learning pre-training process, including how the model generates responses and calculates rewards?
In the reinforcement learning pre-training RPT process, the model begins by receiving a context sequence, x_t, and generates G responses, each consisting of a chain of thought reasoning sequence, c_t, and a final prediction, y_t. For instance, if the context is a mathematical problem, the model might first brainstorm possible approaches, the reasoning sequence, before predicting the next token, the answer. To evaluate the accuracy of the prediction, a deterministic verifier, V, checks if the predicted sequence, y_t, is an exact prefix of the ground truth completion sequence, x_GQT, and whether its length matches valid token boundaries. If both conditions are met, the model receives a reward of 1, otherwise it receives a reward of 0. This reward is then used to optimize the model's parameters, encouraging it to generate more accurate predictions in future iterations.
What theoretical or practical benefits does the RPT method provide over traditional next token prediction models?
The RPT method offers several theoretical and practical benefits over traditional next token prediction models. Firstly, it enhances reasoning capabilities by requiring the model to generate a chain of thought reasoning sequence before making a prediction, which allows for a deeper understanding of the context and the relationships between tokens, rather than relying solely on superficial correlations. Secondly, RPT employs reinforcement learning to verify predictions through a prefix matching reward, which improves the accuracy of next token predictions by ensuring that the generated outputs align closely with ground truth sequences. Additionally, RPT demonstrates superior performance across various difficulty levels in next token prediction tasks, achieving higher accuracy than both its predecessor models and larger models, indicating its effectiveness in capturing complex reasoning signals. Finally, the integration of reinforcement learning in the pre-training phase minimizes the objective gap during post-training, facilitating better alignment and performance on downstream tasks.
How was the performance of the proposed method validated? Discuss the datasets, metrics, and experimental design used for evaluation.
The performance of the proposed method, reinforcement pre-training, RPT, was validated using the OmniMath dataset, which consists of 4,428 competition-level mathematical problems and solutions. The evaluation involved assessing next token prediction accuracy on a held-out validation set of 200 samples, categorized by difficulty based on entropy thresholds, easy, medium, hard. Metrics included next token prediction accuracy, with comparisons made against the baseline models R1 Distill Quen 14b and R1 Distill Quen 32b, as well as the reasoning performance of RPT-14b. The experimental design included continual reinforcement learning fine-tuning with RLVR, where the model was trained on 256 examples and evaluated on 200 test samples, ensuring a robust assessment of reasoning capabilities. Additionally, zero-shot performance was evaluated on benchmarks like MMLU Pro and SuperGPQA, demonstrating RPT-14b's superior performance across all tasks compared to the baseline models.
What were the key results achieved with the proposed RPT method, particularly in terms of next token prediction accuracy and performance on downstream tasks?
The proposed reinforcement pre-training (RPT) method achieved significant improvements in next token prediction accuracy, consistently outperforming the baseline model R1 Distill Quen 14b across all difficulty levels, as evidenced by the results reported in the paper. Specifically, RPT-14b matched the performance of the larger R1 Distill Quen 32b model, indicating its effectiveness in capturing complex reasoning signals. Furthermore, in zero-shot evaluations on end tasks, RPT-14b surpassed both R1 Distill Quen 14b and R1 Distill Quen 32b, achieving gains of 7 points on the SuperGPQA benchmark and approximately 22 points on MMLU Pro. These results demonstrate that RPT not only enhances language modeling capabilities, but also significantly boosts reasoning performance on diverse tasks. Overall, RPT effectively transfers strengthened reasoning patterns to downstream applications, showcasing its potential for improving LLM performance.